All right. Yeah, we're good. All right, question, let's see, homework 5. Libraries in here. All right, what question? 1 or 2?
2.
Question 2. All right. You want to know if fecundity is influenced by any of the 4 independent variables. Check your assumptions. Find the simplest model using AIC. So, just going to make my full model. So we are checking fecundity as a function of site, weight, heat, trematode, metasurface area. That's data. I called it data. And don't know if GBLMA works. Try it. Doesn't. So we are left with looking at the plot. Alright, so just looking at this, it does look like we are reducing. It looks like we have unequal variances. Hold on, let's see here. Looks like we have unequal variances. See how it kind of spreads out. Normality, something funny is happening there. Definitely, you can see the increase from almost 0.5 up to 1. I think we are looking at something that is probably unequal variance, maybe like unequal skew, so skewed in 2 different directions. So that could produce your differences in equal variance and kind of give you an image that's almost normally distributed because of the way they're skewed, one skewed right, one skewed left. Could get something like this type of pattern. So we're going to go with the idea that it's not significant, or that our assumptions aren't met, or we can just be safe. So I'm going to start with the null model because I want my lower. I want to be able to specify my lower. So fecundity is a function of 1. Data is our data file, and then I'm going to go ahead and try to use GeoMulti. So output GeoMulti of, are we going to be able to do mod.null or mod.full? I don't know if we're going to be able to do that. Oh yeah, that works. Yep, pass the full model. After 50 models, after 100 models, definitely makes it simple. That seems to be what our simplest model is. So what I'm going to do is take a look at that weight table. Weight table of our output, which is why we saved it. And this gives our rankings. So it's going to rank it based on the AIC. Actually, we should probably use AICC, right? As our criteria. Nope. Good. Equals AICC, just to be safe. So we'll rerun that, which kind of makes that null model null and void. We don't really need it if we're using GeoMulti. So this seems to be our simplest model, but we'll check it with our weight table. So look at our weight table. We're getting our 100 rows, top 100 models, but we really only need the first couple. And what I want to look at is the AICs. So I can see that we are close. These top 2 models are within 2. The top 2 are within 2. So, and it's close. I mean, this is what, 1.9 maybe? So it's close. So that means we've got site, oligochaete, trematode, and trematode site. that's the simplest model. And then we also have this trematode-oligocete interaction that we could continue to investigate. So it's hard to kind of distinguish between these two models. We could also do that plot, right? It's going to give us the plot that we're looking for. No, what was the function?
Type S.
There we go. Yeah, site oligocete trematode, site trematode interaction. These seem to be the top four. And that, I think I wouldn't even interpret the oligocete trematode because it appears in less than 40% of our simplest models. So I think we have our simplest in that site oligocete trematode, site trematode. So I'm just going to go ahead and mod simp is LM, which is fecundity, is a function of site plus oligocete plus, here, let's redo this. We've got oligocete plus site times trematode. Is that? So that site times trematode interaction will expand out to include the main effects of site and trematode and give me that interaction. So run the mod simp. And now we are on to the post hoc tests. All right. So what do we do with our post hoc tests?
I want to say you're going to subset it into restricted permutational ANOVA.
Okay. So I'm going to go down. The one that we don't have to do is oligocete. Because oligocete is only a 2-level factor. That's it. All right. So what we have to do next to deal with our interaction term is we actually have to take subsets first, and then investigate what's going to be our simplest model. So we can do trematode is yes or no, right? And then our site is 4 levels. So what I can do first is do our trematode subset. Trematode. No. Yes. Trematode. Yes. Make sure we get those right. Yep. All right, so we've got those. All right, so we'll start with the no. So what we have to do is make our model first. So we have fecundity as a function of oligocete. We have to leave that in there. And when we took the subset of trematode, it drops out of the model, which means the only one that we have left is site, right? So data is that.no. All right, now, if our assumptions were met, we could easily just look at the ANOVA table to see if site is a significant predictor. This is the only one that we're looking at, or that we're interested in. All right, so what we can do then is do our restricted permutational ANOVA. You want to see that, or do you want to see the AIC version? Because the other one is just make our new output GL multi of mod.no, right? Crypt equals AICC. Run it. Exhaustive screening of data set. It's not surprising. It basically found all the models, which for 2 variables, 3 variables, it's really easy to do. So now we can just look at our weight table of output. And you can see that it is more than 2. Site is a significant effect. it needs to be included in our model. We could get the same thing with our permutational ANOVA as well. But if we did AIC, we can continue doing that with our subsets. So do you want to see the permutational ANOVA? All right, let me open up my functions. That accidentally closed it. What did I call it? Function script? There it is. Function script. All right, function script. We want our restricted permutational ANOVA. No, where is it? Oh no. I don't have it. Let's download it. Because I posted it, right?
Was it
Announcements. Right? Did it in the announcement. Save that so it's on here. All right, so restricted permutational ANOVA. Paste this in here. So what we found is site is significant. All right, so we have to kind of figure out which sites are different. All right. Site is significant based on AIC. Let's start here. Our data frame that we're working with is dat.no, so we're in the no trematodes. All right. Our grouping variable is a ligate heap, right? This.
Why is it that?
We want to shuffle within a ligate heap, right? We want to make sure that you either, if you have a ligate heaps, you're shuffling within the site only for those snails that have the ligate heap, and then you're shuffling site for only those individuals that don't have the ligate heap. You can think of it as this is going to be that term that we're not interested in testing, but we have to leave it in our model. So we're going to do a ligate heap, and then our null formula is going to be fecundity as a function of a ligate heap. All right, that's our null hypothesis. All right. Is this our right function? Yes, it is. All right, so our test var is site. All right, and we leave everything else the same. So what we're doing is we're kind of doing a little bit of trickery first. So we talked about like the ANOVA type 1, type 2 tables, type 3 tables, and so forth, right? So when we use like a type 2 table, or if we use a sequential table, type 1, when we run our ANOVA, if we just have fecundity as a function of a ligate heap, it fits it, and it accounts for that variation. Well, all the variation that's unaccounted for is hidden in our residuals. So what we then do is take our residuals and we can run another ANOVA where we're looking to see how much more variation is accounted for by an additional variable after we've accounted for that first variable. So that's kind of the basis on how this is being run. So let's try this. I think I have everything. Nope. There. Oh, hold on. Didn't load the function for permute. Is that right? Go with the permute package. All right, so we are starting off with our site. So according to AIC, site's important, we need to include it in. It gives us our lowest AIC, and it's more than 2 units away. Let's see what this gives us. Maybe I should reduce it down to 1,000, make it a little bit more manageable. Significant. There's our p-value. Site has to be left in the model, and now we are going to run. That's all set up. So now, pairwise tests. So we'll do. Let's look at our data. Our site. I think I capitalized everything. Levels, dat, site. Yep, I did. I capitalized everything. So we'll go east and north first. All right. So what I'm going to do is take the subset of dat.no, where site is equal to east or site is equal to north. So everything was all set up. I know it runs. So now what I want to do is only compare east versus north. And to do that, I'm going to make a subset of only east and north, and then when it runs, it's going to give me that pairwise comparison. But the p-value, we're going to have to save that, because we're going to have to adjust it. So once this finishes running, we'll copy the p-value, and I think what we're going to do is we're going to change this down to 1,000, so it's a little bit easier. We can do both of these. Whoa, what? It's still running. Still running. There it is. All right. That's number 1. East versus north. East versus south. Drop it down to 1,000. So our p-value will likely be a little bit different. But I'm just going to rerun this. There it is. East versus west. Oh, and we need to keep track. This is east versus north, east versus south, east versus west. There's it. All right, so we did east. And we're going to go north. We're going to compare south first. North versus south, then north versus west. Change this to west. And this is all if I was doing it on a computer, like in front of my computer, you could probably make different chunks. So that's north versus west. And that means the last one we have is south versus west, right? South versus west. All right. And p.adjust. P-val method is full. So the only one that's not different is this east and south, looks like. All the other ones are different. All the other pairwise comparisons are different. So then we have to repeat it. So that's for the no. Then you kind of have to look at it for the yeses. All right. So I could copy and paste, and then I could just update this and say, yeah, let's do the yes. We'll run our output again. Another situation. We are within about 2. So maybe we need the site and the ligakey. However, we didn't include this. In our global model, we had already excluded that interaction term, so we're not going to put it back. There's no reason to put it back. So if we go to our next model, which is dropping site, well, that doesn't make sense. We know a ligakey is needed in our complete model, so it should stay in there. So we're really looking at this. Should we include site or not? And that difference is easy, what, 10 AIC units? So with the yes, then we just kind of have to go through and do the same thing. Data yes, I'm going to drop this down to 1,000. So our restricted permutational ANOVA is just to confirm this is an alternate way of our AIC selection to see if site is needed. It is, we get a significant p-value, and then we would repeat the whole pairwise things using the yes. So that was for trematode subset. All right. We also then have to go up and do the site. So then what you do is do your north, your north's collecting site, your south collecting site, east and west, and you can do GL multi again. We're just looking to see, do we need to include trematode or not? Maybe, and maybe depending on the site. So maybe we have to include trematode for the north and for the west, but not for the south. And so, but it's tedious. We just have to hit every combination. We have to hit every combination because if we go over to, we're going to do an interaction plot. We want dat $sign site, dat $sign trematode, and dat $sign trematode. Am I missing something? Are the lines just over top each other? Trematode. Factor of 2 levels. See, we're not getting anything here. Someone try an interaction plot on your data set. You didn't have a problem? Oh, well, that's why, because I have all yeses in here. Let me reload my data set. What happened here? Oh, hold on.
You had that as the name for it.
Yes, I did, didn't I?
What if we have the error message need finite lim value?
Yeah, for which one?
When I try to make an interaction plot, it doesn't tell me which one.
So it depends. Do you have your dependent variable listed last?
No, first.
Yeah, so the last one, this fecundity should be here.
Ooh.
That's better. Yes, because I used dat in that function. That could have screwed up some of our p-value. I think that probably screwed up some of our p-value values.
Okay.
Yep, I think it did, because the very first thing we did was did our subset here with dat no, and then we kept doing, well, we did a dat subset for no. No, I guess not, because we didn't use dat again, but we had overwritten dat. So what we're looking at, so the ligakey is significant. What we're trying to do is figure out, number one, are we having different fecundities within east? Are they different in south? Are they different in west? Are they different in north? So So that's kind of the first part of it. And then the second part of it is saying, okay, well, within our solid line, are our points here different from each other? They are. Which ones are different? And we found east and north was not significant. Those two. Is that right? East and south? Yeah, east and south. And you can see these two low ones. Yeah, probably just, we have to look at the data, but yeah, they're different. So if we change the order of our interaction plot, maybe that'll give us a slightly different view. Data trematode. Yeah, so now we can really kind of see it. Nose, no different here, but these are different. And I bet all of these are different. I bet we're going to get significant p-values for each of these. So, I mean, that's the whole reason why we're going through all of these different pairwise tests, is so when you produce a graph like this, you can say which points are different from each other. We know we have a significant interaction, so now we can't really compare, could, but we shouldn't really compare the no of, you know, the west to the yes of south. We really shouldn't be doing that. We know some of those are going to be different because that's the interaction term. What we're interested in is saying, okay, if we don't have the trematodes, which sites are different? If we do have the trematodes, which sites are different? And then within the north collecting site, is there a difference if we have the trematode or not? It adds up. All right, do we need to go on for more, or did we kind of solve it? I know we didn't finish. This is question 2, right? So yeah, I'm hung up on doing all of these post hocs to try to pick out which ones are different. It's on the virus. So just to kind of rehash, and I know we didn't really talk a whole lot, but if we do, I'm going to switch this to no again. Because we didn't overwrite that. So our goal, we're targeting site. So we leave a ligakey in. The ones that we're looking at are these 2 rows. And that AIC is pretty significant. 54 versus 6,400. Pretty significant difference. We need site. Site must be included. Is one way better than the other? Probably not. You just have to be able to explain why you're using AIC selection. All right, questions? You guys saw Cameron's, right? Yeah. Cameron's talk. So we did try GL multi on our full model, and it failed spectacularly. And after the fact, it dawned on me why. Because if you remember in the presentation where I introduced GL multi, I gave you the limits. How many variables, how many parameters you can use. Oh yeah, once you include all hers, it very quickly exceeds that. So it's just like, yeah, I can't do that. But not only that, but if you do a mixed effects logistic regression model, that also kind of runs into issues trying to solve. Because when you have those complex models, you really need probably a couple thousand data points. Cameron has a large data set. I mean, several hundred, it's a lot. But we just kind of ran into the problem. So it happens. And really, there's not a whole lot you can do other than say, you're staying here for 2 more years, working in Houston. It's like, all right, see ya.
Not enough money.
But then,
There's not enough money in the world.
right? It's like, no way.
I'm good.
All right. Ready? If you are doing this in your own research, feel free to come talk to me. We can kind of help you on how to solve it. All right. So, and I am working on the keys to get the keys posted so you can see them. As I said, homework number 4 wasn't meant to use the AIC selection, so you're going to see, I wouldn't print it. No, because you're going to see the 20-some models that I had to make, removing one term at a time and the output associated with it. But it kind of shows you the entire process. I mean, it's basically what AIC selection is doing. It's automated, where I'm doing it, by hand. All right, so we left off on correlations. We talked about Pearson's R, Kendall's Taw, Spearman's Rho. Kind of set up general information. Spearman's Rho is basically Pearson's R, but it's on the ranks. Which ones do we use? Definitely Pearson R works with anything. All right, but if you're going to try to test that correlation to see if it's different from 0, you better make sure that you met the assumptions, that your data are actually normally distributed. If they're not normally distributed, then the fallback's probably, I think my preference is Kendall's Taw, especially if you have smaller sample sizes, but if you have anything more than 48 sample sizes, Spearman's Rho can work as well. All right, so we have these values, you have these correlations, then your advisor looks at you and says, well, is that significant correlation or not? Is 0.2, is that different from 0? How do we go about testing it? Well, we can test it using regular statistical tests. Our null hypothesis is that our correlation value is equal to 0. And this applies to Pearson's, it applies to Spearman's, it applies to Kendall's Taw. All right, so our null hypothesis is that we have no correlation. That anything that we calculate, that 0.2 is just dumb luck. All right, if we took another random sample, we could just as easily get negative 0.2. All right, that's the idea with our statistical test. Our alternative is that it is different from 0. It's not equal to 0. We can do a one-tailed test. So if you go into it thinking I should see a positive correlation between, let's say, length and weight, then yeah, you should probably do a one-tailed test. But if you have no expectation that there is going to be a correlation and then you test it, run your two-tailed test. So our alternate then is that there's no difference. All right, how are we going to do it? Well, the standard method is to use core.test, built-in function. All right, it's built-in function. The standard errors that it uses to calculate p-values makes the assumption that the variables are not associated in any way. All right. So this kind of method, because we're assuming those standard errors, is probably better to have large sample sizes in order to use this test. The reality, though, is that many people use this regardless of the sample size. So when I say large sample size, between two values, you should probably have more than 100 easily to do this core.test. test. But a lot of people don't. So how do we use it? Well, it's core.test. We can give it one of our variables, we can give it second variable, and then alternative and method, where alternative is two-sided, greater or less, if we need to do something other than a two sample test. And then the method is, what method of correlation are we using? Are we doing Pearson's? Are we doing Spearman's? Or are we doing Kendall's? And R will pick it correctly. The alternative way is to use core.test and then write it as a formula where we give it a data and we have the option of specifying subsets and so forth. Now, the core.test isn't written, or the formula for this isn't written as y is a function of x, because we kind of go back to this idea that we're not testing a cause-effect relationship. We're only looking for correlation. So if we're going to use the formula part of core.test, then what you have to do is write it as your squiggly and then the two variables after it, the two variables that you're testing for correlation. All right? So we calculated correlations previously. And the correlations that we did was length and weight. All right, and we had all of those, 0.97, 0.6, 0.84. We shouldn't find significance. Those are super high. But what I want you to do is test to see if those values are actually different from 0. So use core.test, obtain p-values, and do it for all three. Your Pearsons, your Spearmans, and your Kendalls, so we can see the output, and then we'll point out what should be reported in our write-up. What's the what? Formula, I just went over it. Did it work? Did you get output? Hopefully.
What are we considering X1, X2? I guess we don't really.
Length and weight. No, the order doesn't matter. Not with our correlation.
So just all of them?
Yep, just like length plus weight, and then all you have to do is change your method. Ooh, let's fix that. We'll talk about that. So I did it two different ways. Two ways with the formula, all right? And then one way I used the width, because you need data $sign length and then data $sign weight. So just to kind of, again, show alternate methods of doing this. All right, so starting with Pearson's R, it reports a T, it reports a degrees of freedom, reports a p-value. So what it assumes is if we take random samples, then our correlation should be equal to 0. So it's running essentially a one-tailed t-test, making some assumptions about our data. All right, it assumes that we are normally distributed. All right, that's our assumption. Maybe it is, maybe it's not. And you know, if we report it, I'm not sure if I would necessarily report T in the degrees of freedom. I think in the methods you could say we use core.test in R to test it, to assess significance of a correlation, and just kind of be done with that. Report your p-value only. All right. Kendall's tau. Kendall's tau is a rank correlation. It's running basically a z-test, comparing its value to 0. All right. Again, I don't think you need to report the z. Right, that's what it's calculating its average is. It's more important to report that p-value. So it's a small p-value, both of them. And it does. It reports a correlation. So for Pearson's, we got 0.97. For Kendall's tau, we got 0.84. That's the exact same that we calculated when we used the core function. Spearman, same thing. Spearman's testing something a little bit different. Is reporting S as the test statistic. But again, I wouldn't worry about that test statistic. Just report your p-value. Now, we had the question, what is this business about? In core.test cannot compute exact p-value with ties. All right, it's got a problem with it because what we are doing is ranking our data. All right, and it doesn't necessarily know what to do with ties. All right, it kind of throws a kink in calculating p-values. So instead of calculating an exact p-value, it makes an approximation. If you're really concerned about it, we can do randomization tests to kind of generate our own null distribution, compare it to what our observed is. But for this, I'm not terribly worried because our p-values are so small. So one way in which we could write it is, give the test statistic. But again, if you use in the methods section and say I use the core.test function in R, then yeah, skip the S, just report your row or your correlation and then the p-value associated with it. Those are the values that we're interested in seeing.
Forgot. Yeah, stuff covered. So on Kendall's method, why did you have to do that with?
So that way I didn't have to do core.data $length and core.data $width. So or with weight. Let me find our. There it is. Here's our data set. You read it in. Core.data. All right, so in order to use core.test, we could do length and weight, but we have to tell R where it's found, so we would have to do core.data $length, and then core.data $width, or weight, length and weight. Kendall. All right, so we get that output. If we didn't want to use the data $ format, then we can use our width function, which basically says, hey, with this data frame, do this function. So R knows exactly where those variables are because we told it with the width function. So length, weight, method equals Kendall. We'll get the same output. So just, again, two different ways, but in this way we had to, when we don't use width, we have to tell R where those variables are. All right. Minimize it. All right. Standard methods, standard errors were calculated based on assumed approximations. All right. You might not have those assumptions correct. All right. Your data could be skewed. You may have an outlier or two. All right. Now the equations that they use for their approximations are close, but again, they could be wrong, especially if we violate the normality assumption. So I think a more modern method, one that we could be using, probably should be using, is a randomization test or a permutation test. So what this test is basically going to do is calculate the correlation, and it could be anything. It can be Pearson's, it could be Spearman's, it could be Kendall's tau. At this point, it's less important because we're going to generate our own null distribution. So we're going to calculate our observed correlation, and then what we're going to do is generate a loop that makes that null distribution. And what we're going to do is we're assessing the correlation of our variables row by row. All right, the data points row by row. All we have to do is take one of those variables and shuffle it to make it a random association and see what all of our randomized data sets, what their standard correlation is. All right, and then our p-value is just how many values that equal or exceed are observed. So how many values are randomized values equal or exceed the core observed values. So this is the same basis for our permutational ANOVAs, just we're using correlation coefficients. All right, so are the correlations in our previous practice problem significantly different from zero? We know they are based on our assumed standard errors, but we don't know that. So we're going to run a permutation test to address this question. I say you must write the script to run the permutation test. However, on Blackboard I posted it, right? Did you notice it? core.perm.test.r. So here's our permutation test. Move this over. And I've written it so that the output actually reports it as a test. So I called it core.perm.test. So for correlation permutational test. All right, we're going to write it as a formula. All right, with the data set, we can use subsets, specify the NA actions, and the default is 1,000 data sets, or 1,000 replicates. So what it's going to do, the real stuff is here. Starting here, because what it's going to do first is take the formula that we give it and pull out the pertinent information. And then what it's going to do is run the core.test, but we're not going to record the p-value. We're using it because what we want is our actual correlation. And then from the correlation, we're going to shuffle our data set, do it over and over and over again to get our correlation and save that randomized correlation. And then when we're done, we're just going to calculate our p-value, which is very similar to all the other ones. We're counting up the number of values in our randomized data set that equal or exceed the absolute value of our observed correlation. We're adding 1 for actual observed value, all right, and then it's going to report it. So with our core.perm.test, you're going to run the entire function so that it now appears as a function. All right, so get it in R. And it's in our presentation. All right, and then we are going to try core.perm.test. Length plus weight data is core.data. Let's try that. Whoops. I think I have this set up as this. Length is a function of weight. No? Am I missing something in my data set? Length. Why is it invalid? Why is it not working all of a sudden? Don't know why it's not working. Formula missing or invalid. All right. I bet all ears are looking that way.
I just fixed the 1,000.
I couldn't get mine to run as a function. We actually specify the number of runs if there's no formula.
No, we shouldn't. Well, there it is. Yeah, so if we didn't specify it, it runs it. Right? I think maybe I've run into this before. I may have run into this before. I'll have to look to see how we can get it to where we can manually change it in the function itself. But what you could always do is just kind of, yeah, up it in the actual formula itself, and then when you run it, it'll run it. I've run into that before. I think with the permutation, with some of the. I think it was the correlation test. G-test, some of my other functions, I think I ran into that, where it didn't have an effect. So I have to check to see what's going on. Why it's not working. Basically that ends throwing it off for the formula. But this is the output. All right, so this is for Pearson's. All right, it's going to tell you what it's running. It's a permutation correlation test with 10,000 iterations. It tells you the data that it's looking at, so length and weight. It tells you what we're reporting, so Pearson's product moment correlation, and then the p-value. If we wanted to, we can do others using method. All right, so the way the function was set up here is that I didn't have method up here. That's what this ... is calling for. So anything that doesn't appear up here, it's going to look for the extra information, and that extra information is down here for the core.test. It's looking to say, okay, well, what else are we doing? What else are we calculating? Or how are we calculating the correlation? So we can do Kendall's, we can do Spearman's, we can do Pearson's. Default is Pearson's. But we can run all of them. And again, Spearman still gives this problem of, cannot compute exact p-values because we have ties, because it doesn't know how to rank two values that have the same value. So, if you have two weights that are 10 grams, how do we put one in front of the other? It doesn't know how to do it. All right, so we'll have to figure out how to do the ends. So in the presentation itself, I actually give you just a abbreviated code or a shortened code. Much shorter, but that's kind of what the loop is doing. All right, so we're looking at length and weight. We create our randomized variable. We're running this loop where we do our sample of one of the variables, and then we're doing our correlation and saving it. This is just, if you want to do a quick way without having to load that function, this is the basis. This is what we did. But then I kind of put together the script for you guys. I think it looks pretty cool. All right, so couple notes. Prepare for the unexpected. All right, prepare for the unexpected. If you run a permutation test and you get like a really small p-value, you're going to be capped at however many iterations you run. So 10,000, your smallest is going to be 10,000. If you ever get a p-value that's equal to 1, then check your scripts. All right, check your data set. Make sure you're working with the correct data set. Make sure you're working with the variables that you want. All right. This, if you use the script that I give you, shouldn't really happen unless your data set is problematic. You know, maybe you accidentally overwritten one of the variables. Maybe you made a new column in Excel that should have been a formula, but by accident it just copied the second, the column that you're trying to use in the formula. Something like that happens. This is probably you're not gonna encounter this. But if you do a classical test using core.test and then do a randomization, you get some big differences in our p-value. And big differences are looking at big differences is relative to what our p-values actually are. So a difference between 0.01 and 0.02 is pretty small. All right. The difference of 0.04 and 0.06 is actually a pretty big difference because we went from significance to non-significance. All right. But so that's two values. But if you have 0.28 versus 0.3, not really much of a difference. All right. We're looking at 0.28 versus like 0.1. We're getting a pretty big difference. So I give you core.perm.test, you have that. All right, so we do have some practice problems. This is core.csv, this was posted. We already did length and weights. So we have these other variables that we can try. And what this is, just here in class, try to use both classical and permutation tests using these different correlation measures. Just as practice, make sure everything works.
So we don't necessarily have to include use, right? Use.
No. No, about the only time you do that is if you're working with your own data set and you have missing data points. But then you already know they're missing. So then the decision becomes, how do we handle those?
What's the term for the output? Is it a correlation value? Because it's not a p-value. So what is that number? It's
For what function?
For Pearson.
Did you
Or,
use
I mean, any of them, just the number that
Yeah, what function did you use to spit out the number?
core
Okay, so it reports the correlation value. So it'll be,
correlation value.
yeah, Pearson's R or Spearman's rho or Kendall's tau.
Oh, okay.
Get it? All right, so that's how we do structural equation model. You guys have any questions on that? I think math bar. Completely different type of test.
Oh, okay.
All right, so correlation. This, let's see here, length and volume, Pearson. I guess that I'll run both of them. Don't really, if I'm gonna run the test, and I probably would have run the core just to get the correlation to begin with and then say, yeah, let's test it. But it gets reported in both of them. So p-value is significant. Definitely length and volume are correlated. Weight and volume definitely correlated. For Kendall's tau, for food and volume, p-value is 0.12. And now you can see a slight difference. So even with our p-values, there are, you can have slight differences just because of randomization methods. But 0.1262 for the randomization, 0.1217. If we rerun it, we can get a slightly different p-value. 0.1224, you can see it's not changing a whole lot. But in this case, the Kendall's tau is 0.15. That's not different from 0. So even though it's 0.15 units away, it's still not significant. We would conclude that there is no correlation between food and volume. Food intake and volume. All right. Any questions? All right. Tell you what, we will pick up 2 plus continuous variables. So I think we'll do this on Wednesday. This kind of gets at what happens if you've got like our core data set that has multiple ones, and instead of doing it one by one, can we do correlations like all at once? Yeah, we can. So I'll show you how we can do that, and also talk about some of the other aspects of correlation that you should probably be aware of moving forward. All right. So we'll pick this up on Wednesday.
You know when the test is gonna?
Yeah, the application part, I should have it go live on Friday, or at least before the weekend, so you have time over the weekend. And then I think we'll probably have our test on like Monday, Tuesday. That way we can continue on Wednesday with our lectures. All right. Yep.
So I do have a question, and maybe it's dumb, but why do we do the core function when we do core test or the permutational test? It gives us that same correlation coefficient.
So sometimes you run the core just to see what the correlation looks like, and that kind of tells you, well, maybe I need to check to see if it's significant. This is a lot of this, in real life, a lot of this is just exploratory data analysis. So as we add continuous variables to our models, one of the assumptions is that those variables are not correlated with each other. It's like length and weight and volume. We know those are correlated. That we can calculate volume from lengths and weights, or approximate volume from lengths and weights. So if you included all three terms in your model, like in a full model, you violate one of those assumptions of collinearity, meaning you're including terms that are correlated to each other. So one of the first things you might want to do is look at those variables, look at the correlation, and then you can see, oh yeah, volume is correlated to both length and weights. Maybe I should only include volume and not include length and weights to avoid some violations. So I think Cameron did check for association between our variables ahead of time. So that's just something we need to do. So in that case, we don't really need to run the core.test. We could just look at the core to see, well, how high is it? If they're all like below 10, 15, or below 0.1 and 0.15, I probably wouldn't worry about it. But if you start getting into 0.6 or higher, you've got some correlations that